Hello everyone, my name is Xinli. Today I am going to share some experience we have learned about metadata impact for deduplication. This is joint work with my graduate and undergraduate advisors and a few other former co-workers from EMC. I would like to give a quick overview of deduplication. So the basic idea is given an input file, we partition it into chunks, and then we identify duplicate blocks and store only a single copy for the duplicate. And the disk space can be saved by avoiding storing multiple copies of identical blocks. And assume we have multiple versions of the same file, only with a few small modifications across these versions. We are expecting to see a good deduplication benefits. Where in reality, some hidden problem may reduce this benefit. I would like to invite the audience to make a guess about how much deduplication we can actually get for more than 300 versions of Linux source code in the tar format. And let's assume we are using AK average size chunking, and the deduplication ratio is defined as original size divided by post deduplication size. Can you guys make a guess? Well, quite surprisingly, we only get 2 times deduplication ratio. So that means we can only reduce the disk space by half for this dataset. And we did another experiment to examine how much duplicate block actually exists across these source code files. And in that experiment, for each version of Linux, we simply concatenated all the source files together. And quite surprisingly, we actually get 18 times deduplication ratio from that experiment. But you may wonder, what is the problem here? What is the problem with the tar format? Well, to get a better understanding, we need to examine the tar format more closely. The name of tar was derived from paper archive, and its format was first standardized in 1988. So as you can imagine, its format was not designed and optimized for doing deduplication. The tar program collects files into one big archive file, and it has been used widely for file system archiving, source code distribution, and other similar purposes. And we examined the GNU tar format in specific for this study. So a GNU tar file is a sequence of entries, one entry per user file, and each entry contains a header block and a few other data blocks. And in the header block, it contains file metadata, including the file path, file size, and modification time. And assume we have a tar file with including 2 user files. We will have block layout as shown below. So the problem with this layout is the metadata embedded in the header block can be changed much frequently than the data blocks. And we examine the Linux source code. So on this figure, I show the SHA-1 value for the readme file for 2 contiguous Linux source code distribution. And as you can see, we have exactly the same SHA-1 values for this file. However, when we examine the file attributes for this file, we can see the modification time is actually changed across these 2 versions. That will mean we have 2 tar files with exactly the same data blocks, but the header block is changed. Then when we do chunking, we can see chunk 1 and chunk 2 will become different in the second version because of the modification. And how much impact that has for deduplication? It reduces the deduplication ratio by about 8 times, as I have shown previously. So does this problem only happen to GNU-tar format? Well, unfortunately, in reality, we found many other file formats suffer from the same problem, including some file formats used in commercial software, such as EMC Networker or Oracle RMAN backups. And even video files suffer from a similar problem. We can see more detail in the next talk. And the table format suffers from the metadata location change problem. So to deal with this problem, we propose to separate metadata from data. And for the user cases with different constraints, we actually propose 3 approaches. So whenever possible, if it is possible to change the file format, we recommend to change to use deduplication friendly formats, and we use the EMC Networker as an example. When it is not possible to change the file format, we can then do some kind of application level post-processing. This approach is transparent because it doesn't require any modification to program or deduplication system, and we use the GNU-tar as an example. When either of the previous approach doesn't work as a last resort, then we can modify the deduplication system to be aware of file formats, and we use the virtual table library and Oracle RMAN backups as case studies. Because of time constraint, we will only go over 2 user case studies. One is the GNU-tar, and the other is the virtual table library. So for the tar example, I have shown the problem, and the solution we propose is called the migrated tar, mtar for short. It is a new tar format and also a data transformation between a tar and an mtar file. The basic idea is we want to isolate the data blocks from metadata blocks. So, given a tar file, we can do a migrate operation to convert it into an mtar file. And in the mtar file, all the data blocks are stored at the beginning, and all the header blocks are stored at the end. And we store the number of header blocks in the first block. And with the information of the number of header blocks, we can get back the tar file. And this kind of operation is very similar to migratory compression, which is our previous work published in FAST last year. So to evaluate how effective mtar is, we use non-GNU software source code distribution and the Linux kernel source code, and each software has many versions, ranging from 13 versions to more than 300 versions. And the figure below shows the results. So the x-axis shows the data set, y-axis shows the deduplication ratio, and the numbers in red shows the improvement in deduplication ratio mtar brings when compared with tar. We have 2 findings. The first is we see improvement across all data sets. And the second is, for some cases, the improvement are actually quite huge, ranging from 1.5 times to more than 5 times. One thing I want to point out particularly is, even with mtar, we are only getting 10 times deduplication ratio, where I have shown we should get 18 times deduplication ratio for the concatenated case. What is still missing here? Well, the problem is actually even after deduplication, the metadata blocks are still there. So on this slide, I show the percentages of data blocks and the metadata blocks either before deduplication or after deduplication. So as you can see, with entire, we get a good deduplication ratio for the data blocks. We reduce the percentage from 95% to only 6%. We still have the same number of metadata blocks because there is no duplicate in the metadata blocks. So after deduplication, the weight of metadata blocks becomes much more significant, and we need more efficient solution to store metadata blocks. So take your actions. So I have gone over the GNU tar example. Now let's have a look at the virtual table library. What is a virtual table library? It is a disk-based storage system to emulate a table library. When we store an input file into a virtual table library, the table recorder will write the input in fixed size blocks, and it will attach block markers for each block. And the block markers contain some fixed values such as which device and some variable content such as the timestamp of a file, which is when it is written. This encoding schema has one problem, which is the block markers can be shifted because of data insertion or deletion. And here I show an example. So assume we have an input file, and we store it into a virtual table library. It will be inserted as the block markers will be inserted for each fixed size block. Assume we have a second version and we add some new content. Again, we store it into a virtual table library. Block markers will be inserted at the same offset. Then, if we do variable size chunking, we may see that the location of the block markers are shifted. This leads to different chunks, reducing the opportunity to deduplicate against these chunks. I have introduced one solution to deal with the metadata problem for the GNU tar example, and for this, for VTL, I will introduce another approach, which is to modify the deduplication system to be aware of table format. And we can extract the block markers from a table file and store it separately. So giving an input file encoded in a table format, the deduplication system can actually extract all the block markers and store it separately from the date block. And when reading back, these data blocks can be reintroduced before returning the data to applications. How much benefit we can get with this optimization? Well, actually, we have seen an improvement of 75% with this optimization. There's more in the paper, and I have gone over 2 user case studies, and you can read about the other 2 cases in our paper. And the source code of entire is also available publicly at GitHub with the link provided here. To conclude, I have shown the impact metadata has for deduplication. Metadata changes more frequently, introducing many unnecessary unique chunks, and the solution is to separate metadata from data. And we have shown up to 5 times improvement in deduplication. I hope you have learned something from my talk, and do remember, do not let metadata eat away your deduplication. 噔噔噔噔。